Hi students, welcome to Zeta classes. Today we are discussing the first chapter in our class 12 chemistry that is called the solid state. In our class 11, the chapter states of matter, in the chapter states of matter, we already discussed about solid, liquid, gaseous. But there we are mainly discuss about gaseous state and liquid state. So here in this chapter we are discussing about solid state. So here I am just dividing this chapter into three parts. Part 1 we are mainly discussing about two important points. Clear? The first one, classification of solids. Different types of classification of solids we are doing here. And in part 2 we are discussing about, topic 2 in part 1 we are discussing that crystal lattice and unit cell. Very important. The basic part of this chapter. Crystal lattice and unit cell. That's all about the part 1. In part 2, we are discussing about our first topic, the close packing. Close packing in solids. Clear? Ready? And the next one, that is called the packing efficiency. Packing efficiency of solids. Clear? And third one, density of unit cell. We can expect a question for our board examination from density of unit cell. We can expect a problem, okay? And in part 3, that's our final part of this chapter, part 3, we are mainly discussing about the first one, defect of solid, or we can call imperfections of solids. Defects of solids. Ready? And the second one, that is electrical properties. Electrical properties of solid. Clear? Electrical properties of solid. And here we have one more point, that is our magnetic properties. Magnetic properties. That's all about our solid state, okay? So here in this chapter, part 1, we are discussing about classification of solids and crystal lattice and unit cell. And part 2, we are doing the close packing in solids, packing efficiency of solid, density of unit cell. In part 3, we are mainly discussing about defect or imperfections of solid, or second one, electrical properties of solid, and third one, magnetic properties of solid. So I am starting with our part 1. Clear? In part 1, we are discussing two topics, classification of solids and crystal lattice and the unit cell. So I am starting with the introduction of our solids. So in our lower classes, we already studied that the packing of solid, right? We know if we are compared with the liquid and gas, solids are closely packed like this. Clear? Here, the intermolecular force of attraction between these particles is very high. Then we can say they are highly incompressible in nature. And here, we mentioned that here force of attraction is very high due to, we can say, they can show the electrical properties in their solid state. Clear? In solid state, they have no electrical properties. They show electrical properties in molten or aqueous state. Because here only vibration of particles will be occur, only no transfer of our particle will be happen here. Because there are that much of force of attraction between them is present. Here you can see, here these all are fixed. And here only the vibration is occur. Motion of solid state particle of matter, here only the vibratory motion is happen. Clear? So now we are coming to our first part, that is our classification of solids. So on the basis of the orderly arrangement of particles, particles means here constituent particles means we can say that may be atom or molecule or ion, anything. Okay, so here orderly arrangement of particles, solids can be divided into two. The first one, that is crystalline solid, and the second one we can say amorphous solid. Clear? So here we have two classification. First of all, I am just classifying solid on the basis of the arrangement of particles. In the first one is called the crystalline, second one is called the amorphous. So we are starting with our crystalline solid. Clear? So we can just discuss the characteristics of crystalline solids first. Clear? The first point, crystalline solids are homogeneous solids. Clear? And second one, it exhibit long range of order. Clear? You can see here the diagram. I will show you. What is an order actually? Order implies some sort of repetition in structure. So they repeat, or we can say they repeat in long range. Okay? So we can say it exhibit long range order. And somewhat it's like periodicity, okay? We can say that repetition pattern will be going on in case of our crystalline solid. And so we can say long range means it simply implies a continuity. I already mentioned that, you can see here the diagram. In case of crystalline solids, they exhibit long range order, okay? They have same pattern of arrangement in a long range, okay? Then we can say crystalline solids are homogeneous solids and it exhibit long range order if you are compared with our amorphous solid. Clear? Now we can check another property of our crystalline solid. And the next one, we can say they have sharp melting point and definite heat of fusion. For example, in case of crystalline solid, we have an example, that's our ice. Here you can see ice, and in case of ice is an example of crystalline solid. And here we can check the melting of ice, and here melting point is 0 degrees Celsius. Clear? So we can conclude that crystalline solid have sharp melting point and definite heat of fusion. So now we have one more property over here. Here they are given two figure here. In which case energy required to cut the wood is greater? We have one question here. In which case they are showing two figure here. In which case we need more energy? We can simply say the energy is different in two cases, right? You can see the correct answer is it is different. Clear? And for example, we can say here there are many properties which have different values in different direction. Clear? If some cases, in case of some solids, or we can say the values of some properties like refractive index or electrical resistance, like physical properties, values are different in different direction. That is called anisotropic. So we can simply say our crystalline solids are anisotropic. I will explain you how they are anisotropic in nature. That property is called anisotropy. Clear? There are many properties which have different value in different direction. That is called anisotropy. Clear? And we can say, we already mentioned that the first one, they have sharp melting point and definite heat of fusion. Second one, crystalline solid have the ability to change the value of physical properties like electrical resistance, refractive index when measured in different direction. Clear? Such a property of crystalline solid is known as anisotropy. Clear? We already mentioned that. Clear? This is here physical properties like refractive index, dielectric constant, electrical resistance, electrical conductance, everything. Clear? And here, now we can check. Please consider this is example of a crystalline solid. It's arrangement of particles in a crystalline solid. Clear? If I am drawing a line like this, clear, you can see if I am drawing a line like this, here I have the arrangement of particle that is AB, AB. Clear? And if I am drawing the line like this, here the arrangement of particle is AAA type. So here composition of solid changes with direction. Here the composition is AB, AB, right? Here one of its composition is AB, AB. Here the composition in this direction, that is AA, AA type. Clear? So hence the values of physical properties also changes. Clear? Reason for anisotropy, we can check the reason for anisotropy. So this is the actual reason for this anisotropy. Clear? Now we can check what is isotropy. We have one example, that is our glass. Here refractive index of glass is 1.5 in each and every direction. Clear? So here if we can check the refraction of light through this glass slab, here in glass value of refractive index does not change with direction. In case of glass, we can say glass is an example of amorphous solid. Here we can say the values like physical properties like refractive index and any other properties, they are not changing in different direction. Clear? The value is same in all direction. That's why this is called isotropy. Clear? You can see here. composition of solid does not change with direction. Isotropy is exhibited by amorphous solid. We will discuss about amorphous solid again. Clear? So what does anisotropy mean? You can expect a question for our examination. What does anisotropy mean? Exhibiting difference in physical properties such as electrical conductance, refractive index, our electrical resistance when measured along different direction. That is called anisotropy. Clear? Then what is the reason behind the anisotropy? I have already explained with the diagram. Clear? And due to the different arrangement of particle in different direction, that is the reason for our anisotropy. Clear? And now we have MCQ question over here. Which of the following is not a property of crystalline solid? They have sharp melting point, they have definite heat of fusion, they are anisotropic in nature, they are isotropic in nature. Very easy one. You can say they are isotropic in nature. This is wrong because amorphous solids are isotropic in nature. So that is not a property of crystalline solid. Clear? So now I am just listing again the properties. Again I am just showing the properties of crystalline solid. They have sharp melting point and definite heat of fusion. And crystalline solids are anisotropic. We explained very detailedly the reason what is anisotropy and what is the reason for anisotropy and what is isotropy, everything. Okay. And third one, crystalline solids are isomorphous. If you have any confusion in case of isomorphous, you can get the definition here. Isomorphous means two or more substances having same crystalline structure, then it is called isomorphous. So here we can say crystalline solids are isomorphous in nature. Clear? And one more important property in case of crystalline solid, that is, if you are cutting the crystalline solid in two and the newly formed surface during the cleavage, the newly formed surface is very smooth in case of our crystalline solid. Clear? It's not in that property also. So that's all about our crystalline solid. Now we can discuss about our amorphous solid. Clear? Here is the characteristics of amorphous solid. Amorphous means, the meaning of amorphous, that is no form. Okay. Here the constituent particles are arranged in disordered pattern. In case of our crystalline solid, they're well arranged in a long range order. Clear? And here the constituent particles are arranged in a disordered pattern. And second one, they exhibit only a short range order. They are just in, we can say the arrangement is regular only at a small distance, or we can say short range. And there is no repetition. We can connect the term periodicity here. There is no repetition over in case of amorphous solid. Clear? And third one, there are no sharp melting point. Clear? And one more important point here, they exhibit isotropy. We already explained what is isotropy. Clear? And one more important point over amorphous solid, if we cut amorphous solid, we are getting that a irregular surface. The newly formed surface is irregular. But in case of crystalline, that is smooth. And here we have one example, the glass, plastic and everything is under amorphous solid. Clear? And we have the fifth point, on increasing temperature, amorphous solid generally soften and melt over a range of temperature. Clear? Example, tar, plastic, rubber, glass. These all are under amorphous solid. Clear? Now we have one more important property in case of our amorphous solid. Clear? That we already discussed in case of our states of matter chapter, class 11. Here, like liquids, some solids mean, now we can crystal clearly we can say that is amorphous solid. They have tendency to flow to very slowly, therefore sometimes these are called pseudo solids or supercooled liquids. Very important one. Clear? So like liquids, some solids like our amorphous solids have tendency to flow. Clear? This property is called pseudo solids or supercooled liquid. Here these lines you can see in our viscosity point in our states of matter chapter, and here glass pans fixed to windows or doors of old buildings are slightly thicker at bottom than top. So if we are checking the old buildings, you can see here their glass pans have more thickness at bottom part if you are comparing with top part. That means glass is an example of amorphous solid, right? So here the molecules are slowly moving, right? Like liquids, they have tendency to flow. Clear? Due to this property, we can call them pseudo solid because solids are closely packed. There are no flow of molecules there. But here, in case of our amorphous solid, they have tendency to flow. That's why they are called pseudo solids or supercooled liquids. Clear? So I'm just reading again this. Glass pans fixed to windows or doors of old buildings are slightly thicker at the bottom than at the top. This is because the glass flows down very slowly and make the bottom portion slightly thicker. Clear? It's actually false solid, right? We can call amorphous solid false solid or pseudo solid. And amorphous solids on heating become crystalline at the some temperature. Some glass objects from ancient civilization are found to become milky in appearance due to some crystallization process. Clear? So here amorphous solid on heating become crystalline at some specific temperature. Okay, please note it down. And here is our differences. I am just summarizing the difference between crystalline and amorphous solid. And first of all, we are talking with our shape. Crystalline solid have definite characteristic geometrical shape, and in case of amorphous, from the name we can getting, they have irregular shape. Clear? And in case of melting point, crystalline solid they melt at sharp and just characteristic temperature only, but amorphous solid gradually soften over a range of temperature. And now we can check the cleavage property. When we cut with the sharp edge tool, they split into two pieces, and the newly generated surfaces are plain and smooth in case of crystalline solid. But here, when cut with a sharp edge tool, they cut into two pieces with irregular surfaces, for example, in case of glass. Okay, so now we can check heat of fusion. They have a definite heat of fusion, but in case of amorphous solid, they do not have definite heat of fusion. And we already discussed that anisotropy, and in case of crystalline solid, they are anisotropic in nature, but in amorphous solid, their physical properties is same in different directions, so we can call their isotropic in nature. So here, order of arrangement, we can say in case of crystalline solid, we already seen the diagram. They have a long range order, but here the only short range order is present. Clear? So these are the difference between our first classification, that is our crystalline and amorphous solid. Clear? So now we can check a MCQ question over here. Here amorphous solid are option A disorder, long range, disorder, short range, ordered, long range, ordered, short range. It's very easy one, right? We know amorphous solids are disorder and they are short range in order, so option B is correct answer. Clear? We have one more question. The following is an example of amorphous solid. Glass, rubber, tar, all of this. Clear? All are examples of amorphous solid. Clear? We have one more question here. Amorphous solid is A, it has no sharp melting point, soften on heating, exhibit isotropy. All of this. All are the properties of amorphous solid. Clear? So now we can check the classification, the further classification of crystalline solid. So based on the force of attraction between the particle, constituent particle, I'm just classifying crystalline solid into four. The first one is called, here you can see, the first one is called the molecular solid, second one is called ionic solid, and third one is called the metallic solid, and last one is called the covalent solid. This classification is based on the attraction between constituent particle. Clear? And here, first of all, we will start our discussion with the molecular solid. And this molecular solid further classified into three. The first one non-polar molecular solid, and second one polar molecular solid, and third one hydrogen bonded molecular solid. So we are starting with a non-polar molecular solid. Here atoms like argon, krypton, etc. And here we can say molecules formed by non-polar covalent bond. Here, for example, in case of hydrogen, we can say in case of hydrogen, there is no charge separation, right? We know that, we already discussed that in our chapter chemical bonding. So we know if hydrogen, clear, each have one valence electron, and here they are mutually sharing the electron, right? They are mutually sharing the electron. Clear? Then we are getting this bond. Clear? Actually here the electronegativity difference here for both hydrogen, that's 2.1, 2.1. And here there is no we can say if electronegativity difference is equal to 0, they are non-polar covalent bond. Clear? So here the attraction is non-polar covalent bond. Here is the example H2, F2, Cl2, Br2, I2 and N2. Clear? And example is very important. And these solids are soft and non-conductors of electricity. They have low melting point and either liquid or gases at room temperature and pressure. And the atoms or molecules are held together by here weak dispersion forces or London forces. London force discovered by Fries-London. Clear? And here in case of non-polar molecular solid, the force of attraction between them is dispersion force, or we can say London force. Clear? Now we can check the second one, that is called the polar molecular solid. Polar means actually they have permanent dipole moment over here. For example, in case of HCl, the electronegativity difference is, we can say in case of hydrogen, electronegativity is 2.1. In case of our chlorine, electronegativity is 3 or 3.5, around 3 into 3.5 range. Clear? So here they have covalent bond, they have covalent character, but that is a polar. Clear? Because there is already a charge separation over there. Hydrogen have partial positive charge, chlorine have partial negative charge. So there we can say this this type of molecules is called, their solids are called polar molecular solids. They contain molecules formed due to the polar covalent bond, example HCl, HBr, SO2, NH3. Examples are very important. We can expect for that for MCQ questions. And these are soft solids, and they are non-conductors of electricity. Their melting point are higher than those of non-polar molecular solid. If you are comparing with our first one, their melting point is very high. And most of these are gaseous or liquids at room temperature and pressure. And these solids, molecules are held by strong dipole-dipole interaction, because here they have permanent dipole moment, right? Clear? In case of here, hydrogen have partial positive charge, here chlorine have partial negative charge, and they have the dipole moment. Clear? So we already discussed that in our class 11, because we know here they are showing polar covalent bond and they have permanent dipole moment, and here the interaction is permanent dipole-dipole interaction. Clear? But in case of our first one, the interaction is very weak very weak dispersion force, or we can call the London force. Clear? Now we can check the third one in our molecular solid, that is hydrogen bonded molecular solids. And here the molecules of such solid contain polar covalent bond with a hydrogen and fluorine oxygen ion. We can simply H-phone, right? H-phone. Hydrogen just forming bond with electronegative element like fluorine, oxygen, nitrogen. That is H-phone. Okay, clear? Please remember using that code. Clear? And here they have strong hydrogen bonding, binds molecules of such solids like H2O. So H2O in ice. Clear? H2O is a solid form in case of ice. Clear? So here this is example of hydrogen bonding molecular solid. And they are non-conductors of electricity because they are closely packed, right? Clear? So that's all about our first one, molecular solid. Now we can just recall their parameter and properties in case of a non-polar, polar and hydrogen bonded. So here we discuss about their constituent particle, and here we can see the examples. For example, in case of non-polar, we can say the constituent particle is non-polar molecules. In case of polar, the constituent particle is polar molecules. In case of hydrogen bonded, here the constituent particle is hydrogen atom and the most electronegative atom. Please remember our code H-phone, okay? And here the example, in case of non-polar, we have example H2Cl2, He, neon, carbon monoxide, etc. In case of polar, we have, if the compound which is having permanent dipole moment, these all are the examples of polar. Clear? SO2, HCl. And here, in case of hydrogen bonded, we have example H2O and HF, and H2O is present in the form of ice, okay? And nature of interaction we can check. In case of non-polar, we already discussed that London force or dispersion force, very weak. Okay. In case of polar, we have dipole-dipole interaction, and in case of hydrogen bonding, we can say here strong H bonding is present. So due to presence of this H bonding, it have high boiling point and all. Clear? We will discuss that. And in case of our state, we can say non-polar exists in gas and liquid, and polar exists in gaseous state, and hydrogen bonded exists in volatile liquid. And in case of nature of solid, we can say non-polar is very soft and polar is soft, and hydrogen bond are also soft. So we can conclude, say, molecular solids are very soft in nature. And their melting point, in case of non-polar solid, we can say that lowest melting point. In case of polar, they are also showing greater than that of non-polar, right? And here, in case of hydrogen bond also, that is greater than that of polar. Clear? And conductivity range, non-polar solids are non-conductors, and polar also non-conductors, hydrogen bond also non-conductors. They all are non-conductors of electricity. Clear? So that's all about our first type, that is molecular solid. Clear? So we have one MCQ over here. Which of the following is not a type of crystalline solid? Option A, molecular solid. Option B, ionic solid. Option C, covalent solid. Option D, non-metallic solid. Clear? So here we have the option, that is our non-metallic solid. Clear? Now we can discuss in case of our ionic solid. Clear? So here we have the structure of ions. So we know in case of ionic solid, they consist of two important ions. The first one is cation and second one is anion. And we already discussed in our class 11 classification of elements, due to the addition of electron, this anion have more size due to repulsion. Clear? So if we are combining anion and cation have more size than cation. Clear? And here constituent particles of ionic solid, we already discussed that. Here we have a small size cation and a large size anion, and cation have positively charged and anion is negatively charged. So these two are the constituent particles in case of our ionic solid. Clear? Now we have example NaCl, KCl, etc. Clear? So here I am taking an example of NaCl, that is an example of our ionic solid. Here we have the positively charged Na plus and negatively charged Cl minus ion. This is anion and this is cation. Clear? And here you can see the two-dimensional and both three-dimensional arrangement of this lattice. Okay, that means our arrangement. Clear? This is a crystal lattice of our NaCl, but this is in two-dimensional and this is in three-dimensional. You can see here the cations and anions are arranged. Clear? And by looking in this 3D diagram, you can say cation have small size if you are comparing with our anion. Clear? And the third point, ionic solids are formed due to force of attraction between the ions of opposite charges. That means here we have the opposite charges between this cation and anion, right? So here, that's why here the bond is forming. That's why the solids are forming. Clear? And the force of attraction between the ions of opposite charge, we already mentioned that in the structure of NaCl, number of Na plus equal to number of Cl minus. We will discuss that during the study of crystal lattice. And the total charges in ionic solid are well balanced, hence they are electrically neutral. If we look at any phase of this NaCl, you can see here, if we are checking this phase, we can say anion is surrounded by cation. Clear? If you are taking any phase of this NaCl crystal, here you can see this anion is surrounded by cation, right? And similarly, cation also surrounded by anion. You can see here. And such arrangement of ions depends on, clear? And we can say similarly, this cation are also surrounded by anions. So we can say they are electrically neutral. And similarly, cation are also surrounded by anion. Clear? Such arrangement of ions depend on three factors. The first one, size of ion. Second one, charge of ion. Third one, extent of polarization of anion. We already discussed the polarization concept during our Fajans rule discussion, right? Polarization is the ability of our anion. Clear? This is we discussed during the covalent character in ionic solids. Or ionic, we can say ionic compound have tendency to share electron. That is called that explained by Fajans rule, right? There we discussed the term polarization. So here, if extent of polarization of anion, charge of ion, and the size of ion, these all are depending the arrangement of our ions. Clear? So this is the structure, or we can say crystal lattice of our NaCl structure, NaCl crystal. Clear? And now we can check some important properties of ionic solid. First one, ionic solids are very hard and brittle, and ionic solids have high melting point. And third one, ionic solids are non-conductor, or we can say poor conductor of electricity. And ionic solids in the fused state or molten state or aqueous solution, they conduct electricity. Because in solid state, we can say ionic solids are closely packed, right? There is no movement, only vibration of our ions are there. So here, in fused state or molten state, or we can say in case of aqueous state also, they can conduct electricity. Clear? On application of a shear force, you can see a shear force, that means the repulsion between them. Clear? And these crystals undergo distortion and are just fractured. In case of ionic solid, due to the application of this shear force, these crystals, the ionic crystal undergo distortion and we can say fractured. Clear? Now we can check our next type of solid, that is called the metallic solid. Okay, metallic solid, we can see here metal atom is present in here, and this metal atom is consist of electron actually. And here we have a sea of electron is present. You can see here metal have low ionization potential. That means energy required to remove the most loosely bounded electron valence shell is very low. Clear? And here, since metal have low ionization potential, they lose electron very easily. We know that very basic concept, right? In case of metals, they have very less amount of ionization enthalpy required because they are just ready to lose electron. So they need very small amount of energy. Clear? And here you can see this metal ion is called a kernel, and here this free electron, we can say free electron or mobile electron, or we can call the delocalized electron. Clear? So for examination they are asking what is kernel. This metal ion is called the kernel, and that's surrounded by free electron, or we can call the mobile electron. Clear? And or we can call here sea of electron. The constituent particle in metallic solids are this is both, okay, this metal ion and this sea of electron, clear, or we can call the free electrons, clear. And we can check some important properties of metallic solid. First one, the constituent particles in metallic solids are metal ion and free electron. Second one, the force of attraction between the kernel and free electron is metallic bond, clear. We know the kernel, that means our metal ion have positive charge and this electron have negative charge. So there is a force of attraction between that bond is called a metallic bond. And they are good conductors of heat and electricity. We know metals, right? Metals are good conductors of electricity. And fourth one, they are hard, malleable and ductile and sonorous also. These all are the properties of metal, clear? And fifth one, they have high melting point and boiling point. They possess luster and color also, clear? And they have the property sonorous also. We can say they are sonorous. They make sound if we are hitting on hard surface. Clear? Ready? So now we can check MCQ question here. Metallic solid consists of option A metal ion, option B kernel, option C mobile electron. Clear? And option D all of this. Clear? So it consists of this metal ion is also called kernel, right? So this option D is the correct answer. All of this. And we have a second question, kernel is. Kernel is metal ion, right? Kernel is metal ion. Option A is correct answer. So now we can check our fourth one, that is called covalent, or it is also called network solids. Covalent solids are also called network solids. We can check some important properties of our covalent or network solid. The first one, these are non-metal crystalline solid from the formation of covalent bond between the adjacent atoms throughout the crystal. Adjacent atom throughout the crystal. Clear? This actually we can call, they are giant molecules actually, like diamond, graphite. These all are under covalent or network solids. Clear? So covalent bonds are strong and directional. And we can say these solids are very hard and brittle. Covalent solid, we can say these network solids are very hard and brittle. They have extremely high melting point and we can say it may decompose before melting. Clear? And they are insulators and do not conduct electricity, but in case of graphite, they conduct electricity. We have an exception of here. Clear? Example, diamond, silicon carbide, or we can say aluminum nitride, graphite, each and everything. That is all under our network solids. Clear? And here it's a structure of diamond actually. And here each carbon atom is shared with the other 4 carbon atoms. That's why it's very, very strong. Diamond is actually an allotrope of our carbon. Clear? And here, one important exception here, graphite conduct electricity and graphite is very soft in nature. Diamond is very hard. Clear? This is a network structure of solid, diamond. Clear? And I already mentioned that graphite is a soft, solid conductor of electricity through its network solid, and free electron in graphite are responsible for good conductivity of graphite, or we can say graphite has layer lattice structure and which is responsible for its lubricating nature at higher temperature and due to the strong covalent bonds among carbon atoms. Clear? Graphite have a layered structure. Due to that reason, they act as a good lubricating agent in high temperature. And we know in case of graphite, we can say here each carbon atom is shared with the other 3 carbon atoms. Clear? So there is a free electron present in case of our carbon present in our graphite. So this free electron is responsible for the conductivity nature of our graphite. Clear? You can see here the structure of graphite. It have a layered hexagonal array, right? So it have a layered structure, and here each carbon is connected with only 3 carbon. You can see here each carbon is connected. If I am just taking this carbon, it's connected, shared with only 3 carbon, and due to the presence of that valence electron, it can conduct electricity. Clear? You can see the structure here. They form the layer by layer. Clear? So now we can just conclude. For examination, you must learn this only, okay? Because that must take time to remember every point. So I am here just mentioning the important point only. So here we are just classifying molecular solid, metallic solid, ionic solid and covalent solid, and the constituent particle in molecular solid, that is molecules. Clear? In case of non-polar molecular solids, that is non-polar molecule. Here polar molecules, here hydrogen bond molecules. And we discussed the force of attraction. In case of ionic solid, we have electrostatic force of attraction between that oppositely charged ions. That is called the Coulombic force. Clear? In case of metallic solid, we have metallic bonding. In case of covalent solid, we have covalent bonding. And these are the examples. At least remember the examples, okay? That's very, very important. They just give example and they ask which type of solid is here. And here is the physical nature and is the electrical conductivity, and we can check their melting point also here. So this table is very, very important. This table is from NCERT textbook, okay? So that's all about the classification of crystalline solid. Now we discuss about the molecular solid, our ionic solid, metallic solid, and finally covalent solid. This is a summary of this classification. Clear?